Hello everyone, today we'll talk about the solution to the problem maximum sum of 3 non-overlapping subarrays. Don't worry about the classification of this problem as hard. As you can see from the length of the solution, which essentially starts at line 7, the solution is short, and I can assure you it's not that difficult. Let's go over the idea that's probably the easiest one when solving problems like this. Now, we have to choose 3 non-overlapping subarrays, maximize their sum. So we can imagine that we take some subarray, let's say the last subarray that we select, then we have selected it, we have it in our sum, and the remaining sub-problem is that we have to select 2 more subarrays from the prefix before that last array that we've chosen. And then we choose the second array, and we have to choose the remaining first array from an even shorter prefix. Or maybe if we prefer to look at it from the other way, we have to first select the first subarray, and now we have to select 2 subarrays from the suffix that remains. So we can do exactly that. We can just remember for every position and for every number of either used or remaining choices to be made, right? Subarrays to select. We can remember the best result that we can get. And so, if we have this dynamic programming, which here will be just implemented using standard recursion, where we make a binary decision, either we take this block or we don't take this block, but because we can use the cache decorator for easy memorization, this is actually dynamic programming and not just this, let's say, straightforward recursion. By the way, to make things a bit easier for us, since we want to find sums of subarrays, we can pre-calculate them if we want. We can use a sliding window, but we can also just calculate prefix sums. And in that case, if we have calculated prefix sums, probably more readable is to do it manually, but you can also use accumulate like this, and add is from the operator library, from the operator module. For prefix sums, because now if we want to take the subarray ending at position I, its sum is prefix sum of I minus prefix sum of I minus k. So the prefix sum up to the end of our subarray minus the prefix sum that ends before the beginning of our subarray. So this is the value for our array. So the function will be taking the position at which we're deciding whether or not to take the k elements ending at that position or not take them, and the number of remaining subarrays that we have to select. So if we don't have any subarrays to select, or we cannot fit a subarray in the prefix that remains, because I'm going to be solving this problem starting from the end, from the last value, that's the same way that I explained it at the beginning, we just return 0. We also have to remember, because we have to remember both the list of indices, and we also have to make sure that we return the lexicographically smallest one. So we have to remember both the score and the split that generates that score. So it's just an empty list, and score is 0 if we cannot select any subarray. And now our decision. We either don't take that subarray, so we have the same number of remaining moves, and we just decide to ignore this number for now and look at the prefix that's one shorter, or we take that value, so we have to jump k elements back. We have one fewer remaining subarray to select. Those are our 2 options. Of course, if we take this subarray from I minus k to I, we have to increase the total by its value. That's what we've done here. And we have to add our decision to the list. I'm writing it like this instead of append because, of course, lists are passed by reference. This cache will remember them by reference. So if we just wrote indices 2 dot append I minus k, then we'll be modifying too much. Instead, we want to make a copy. This forces us to make a copy. This addition makes a copy. And now we can select the better option of the 2. So the option that gives us the better total. And we just return it. So we either return total 2 and appropriate indices or total 1. And now here we just have the greater than sign. And that guarantees that we'll find the lexicographically smallest solution, since we also make the decision of ignoring the element first. So both the order of these lines is good for finding the lexicographically smallest one, and this equals sign. This equals sign makes it so that this total 2 will never override total 1 if they are equal. So this first line takes precedence. And this first line is the one that essentially pushes the decision back into the prefix, so into the lexicographically smaller possible results. So we have to finally, to wrap this all together, we have to run our function. We have all the numbers remaining, so we just pass len of numbers as the position. And we have 3 subarrays to select. So notice that the fact that this is free doesn't really matter. The solution will be the length of the time complexity will be the length of nums times this 3 parameter. And of course we don't care about the total, we only care about the indices. So we just return the second value, so the value at index 1 or the value at index -1. It's the last value from the returned value, the returned pair in this case.